Okay, so welcome to week 8 of the fundamentals of nano and quantum photonics course. And uh, I'm pre-recording this session so that you guys can at least watch it over the YouTube. And this course is being offered by NPTEL in collaboration with IIT Hyderabad and IIT Madras. And the course instructor is Professor Naresh K. Imani. And I'm Shazan Bhatt, and I'm a direct PhD student at IIT Bombay and Technical University of Berlin. So, what we are going to see today is that we are moving into week 8 of this course on fundamentals of nano and quantum photonics. And this will be the course, this will be the session outline for today. And we'll be trying to define how the light matter interaction takes place from a quantum mechanical picture, considering the two levels, the ground state and the excited state. And we are going to see the dynamics, the time-dependent solutions of the evolution of probability distribution of the ground state population and the excited state population. So one thing I would like to clarify is that whenever I'm talking about the ground state population or the excited state population, we are either talking about atoms or we are talking even about electrons. So it applies to both of the cases. So when I'm talking about some species in the ground state, it can be some atoms in the ground state, or it can be even some electrons in the ground state. Okay, so that applies to both of the cases. So here, right here, we are only talking about two levels in order to simplify the system and to apply and solve some of the time-dependent Schrodinger equations in order to understand the evolution of probabilities of the population. Then we will try to define something called as Rabi oscillations. We'll go into the strong and weak coupling regime. We'll talk about something called as Purcell factor, and then we will try to go into the quantum mechanical picture of an electromagnetic wave. So how we go from electromagnetic wave to a single photon, wherein you have the totally different rules governing the motion or the dynamics of the single photon. Okay, and how you can generate the single photon, what is the procedure, what are the applications of a single photon source, how you can control that single photon source on demand, and what are its, I should say, properties. That is what we are going to see. And these are the references I have been showing in from a couple of weeks now. And again, I'm going to follow the similar trend wherein I would try to remain concise as possible, so that we can just stay on the topic. And wherever I would annotate using the red color or any other different color, that would be, I should say, the overlay over it. And I'll try to explain a few more things, whatever the professor might have explained in his lectures. And you can go through these notes and you can just, these are just short notes where you can revise your concepts and apply the same in your problems, which are directly derived from these particular lectures even. So here, what basically in the first week, what basically we have tried to cover is this is week 8, and this is lecture first of what we have tried to cover something called as resonant light atom interaction. So how the light behaves or interacts with the two-level system. When we are talking about the two-level system, we are talking about some kind of a ground state and some kind of an excited state. Where in the ground state you can have a ground state population of the atoms, and once they get excited, you can consider them to be excited state population of the atoms. And similarly, we talked about in the previous sessions, we talked about the absorption, we talked about the spontaneous emission of the photons, and in the actual sense, when you talk about the energy levels, what are these energy levels? These energy levels are nothing but they are the distribution of the wave functions in an atom. What do you mean by that? Let's say, for example, you have a quantum well. Okay, all of you know that if this is a, let's say, infinite potential well, infinite potential well, or what you call as, let's say, quantum well, but it's an infinite quantum well. That means the the potential inside is zero and outside it's infinite. So let's say this is the potential. And what we are going to see is that, let's say this is x. When you solve the Schrodinger equation, and when we are talking about the Schrodinger equation here, this is time independent Schrodinger equation. So you solve something like maybe you might know you solve something like minus h bar square over twice m dou square psi over dou x square, only considering the single dimension, plus v of psi equals to e of psi. So there is no time variable in this particular thing. There is no time coordinate in it, here, in here. It's only a space dependent quantity or space dependent equation showing the variation of the wave function in the space. And you simplify it, you write something like dou square x over dou x square minus something like twice m over h bar square v minus e of psi equals to 0. You solve this differential equation using the potential v equals to 0 inside, and you get these levels, which are n equals to 1, n equals to 2, n equals to 3, so on and so forth. And as you go higher, the spacing between the two levels go on increasing. So that is the basically the solution of Schrodinger equation. The solution psi of x will be equivalent to some there is some factor a sine of n pi x over, let's say this is the width L, so n pi x over L. So this is the solution of the Schrodinger equation, where n is basically the even 1, 2, 3, or so on and so forth. Basically, it's some positive integers. Okay, so you know about it. Now, what do those levels represent here? The levels, these are basically different forms of the wave function. So let's say for n equals to 1, you get the wave function to be of this form, not this. You get the wave function to be of this form, and for n equals to 2, you get the wave function of this form. For n equals to 3, you get the wave function of this form, so on and so forth. So these energy levels are basically the shapes or the distributions of the wave function in this quantum well. That is it. The concept of energy is abstract. You don't have any levels as such. You cannot see any levels. These are just how the electrons are distributed in an atom or in a quantum well or in any of the electronic lattice or atom. Okay, so that is basically what energy levels we refer to here. So these are the distributions or the probability distribution, and this is, let's say for example, this is psi of x. If you compute something called as mod psi x square, you get the probability distribution function of a wave function. And for n equals to 1, it will be something like this. When you, let's say, when you square it, you get sine square of n pi x over L. So it will be something like this, something like this, something like this. Okay, so because the negative will become the positive. So this is the this is mod psi square x, mod psi square x. So this tells you the probability distribution of the electrons inside a quantum. Similarly, you can do it for even an atom. If you have, let's say, for example, an atom, and if you consider, for example, the simplest atom, the hydrogen species, the hydrogen atom, with a single positive charge and an electron, with electrons wave function around the nucleus, which is spherically symmetric. And we consider it to be in S state. Obviously, you might be knowing the electronic configuration of the hydrogen atom. It's 1s1. So this S is basically the how the electrons wave function is distributed around it. So you might see when you compute the, let's say for example, if you solve the Schrodinger equation for it in, let's say, spherical coordinates, you solve the Schrodinger equation in spherical coordinate system, considering, let's say, this is some r, some theta, and some phi. Okay, so you solve it in spherical coordinates, the same differential equation, this one in spherical coordinates, you get the wave function values. Okay, what you get? You get n, l, and m quantum numbers. That is what exactly you get. So you get n, l, and m, which basically represent the principal quantum number, azimuthal quantum number, magnetic quantum number, and then there is s spin that comes from a different perspective. But that is basically, these quantum numbers are the solutions of the Schrodinger equation you get, and that's why you have been talked about these quantum numbers in your basic classes, let's say 10 plus 2 or 10 plus 1 classes, where you studied atomic structure, maybe in chemistry, if you remember correctly, in 10 plus 1 level. So, but these are the solutions of the Schrodinger equation. And it's not as simple as that. I'm just trying to bring it down to a layman level so that you can understand where it comes from. But what I'm trying to say, the same role here, what when you get this particular n in the quantum well, that is basically a quantum number. Similarly, if you talk about, let's say, a solid, when you solve the Schrodinger equation for a solid, you get a band structure. Obviously, you need to consider the chronic Penny model, the Bloch's theorem, the periodicity of the atoms in a solid. Let's say this is a solid, then you need to consider the periodicity and all other things. You need to consider the Bloch wave function. But what is the solution you get? You get the solution in the form of, let's say, you get some kx, ky, kz, where these are the wave vectors of the electrons. These are the wave vectors of the electrons. Okay, in K space. But in actual sense, these you get these from the solving the Schrodinger equation in three-dimensional, 3D. So considering this to be a 3D crystal, let's say this is x, this is y, this is z, then you get kx, ky, kz, which is basically comes from the Schrodinger equation. And this kx, ky, kz in the solid plays a similar role what n, l, and m plays in an atom. So these are basically the quantum numbers in a solid. These are basically the quantum numbers in solid. Quantum numbers of what? Electron. So that is the fundamental thing you need to understand and think about. What is the relation between how do we go from an atom to a quantum well to a solid with n number of atoms wherein there is some repetitive arrangement or the periodicity. So that's what I wanted to explain here. Now here what we are considering is that we are considering some system which has basically only two levels, and it's either going to absorb, it's either going to have spontaneous emission. Now, what do we do? Here, you only solve the time-independent Schrodinger equation. Now, if you want to see what happens if you give some time-dependent perturbation to two-level systems, because you know that you have some kind of a time-dependent electromagnetic wave, which is having a space as well as time dependence. You write the electromagnetic wave something like e to the power I omega t minus kx. So it naturally has t, it naturally has x in it. Okay, so it's a time and space varying thing. And when it interacts with the system, there is going to be a spatial as well as time dependent dynamics or evolution in the states. So that's why we need to, for this problem, we need to solve the time dependent Schrodinger equation. So there is no other way out because you need to see what is the evolution of the wave function in space as well as time. So you need to, I should say, understand what is psi of x comma t. Or in other words, if you, let's say, for example, consider a two-level system, let me just use the red. If you consider the two-level system shown here, wherein the lower level has energy E1 and it has N1 number of species present in the lower level. Similarly, a higher energy has E2 energy and number of species is N2. So these are almost like a quantum states. And you know that if you have a quantum states, you can define its wave function. That means what is the probability? The wave function square will give you the probability distribution of those species. Right now, I'm talking about just species. It can be electrons, it can be atoms, it can be even photons, it can be even phonons. Okay, so that's a different story. We're talking about the species in general. So you have the wave function. Let's say it's represented by this Dirac notation, which is represented by this ket of n. Okay, so it's a bracket notation represented by this. So that if you are let's say for example ground state, if your species is in ground state, then it can be represented by this. If it's in excited state, then it can be represented by this. So it's like a wave function or one wave function two. So it's a wave function of an species in level one, wave function of species in level two, so on and so forth. So we know from the basic quantum mechanics, because the basic quantum mechanics is the prerequisite of this course. You see, the elementary quantum mechanics comes in the prerequisite of this course. So I hope you guys know about the basis states, about how you can expand any of the wave function in terms of the basis states. So you can write a wave function for this two-level system in terms of some coefficient times that particular wave function. So it's like, almost like C1 psi1 plus C2 psi2. So you can write the overall wave function to be the linear sum or the linear superposition of the wave functions of first state and the second state. So it's almost like the adding the overall the probability and the wave function in one times the probability and wave function in the second. And what happens now is that if you want to find the probability of the wave function in state 1, then you simply have that probability, which is basically the square of this particular coefficient. So you get the probability of wave function in state 1 and state 2 to be C1 square and C2, mod of C1 square and mod of C2 square. So you can find it by any other means. You can just if you want to find the probability, you can just write you can just multiply that particular state to both sides of this particular equation, and then you get the C1 square and C2 square. That's just whatever you have studied from the elementary quantum mechanics. And now the important thing is that if you consider this if you consider this quantum mechanical picture with that of the classical picture, which is basically shown here on the left hand side. In the classical terminology, if there are total number of atoms, let's say n naught, atoms or species, if there are total species n naught, then these species are distributed in two levels. So n naught is distributed in n1 and n2. So that total species is basically n1 plus n2. And the probability of finding species in one level, that will be C1 square, and this will be C2 square. So that will be given by number of species in level 1 divided by total species. That is the simplest, I should say, probability. You can find it. Similarly, for C2 level, it will be given by the number of species or the atoms in level 2 divided by total number of atoms. So it's almost like a statistical mixture. And here we are not considering any interaction between the atoms. That is the important thing. We are considering them to be independent of each other. We are not considering any effect of level 2 on level 1 or vice versa. So that is the important thing. We are not considering any interaction here, or we are considering to be totally independent. But what happens if you consider them to be dependent? That is what happens. You treat that quantum mechanically. Okay. Now, in order to do that, if there is, let's say, there are two states and there are some phases associated with the species. You know that if you have an electron that is moving through the solid, there is some phase associated with it, which is given by e to the power I k x phase, or e to the power I k a, where a is the periodicity. So you consider them, if you consider the lattice sites to be almost like a potential wells, then if you know what is happening to an electron here, you can pretty much know what is happening to electron here, what is happening to electron here. Only the difference is that there will be some phase vector associated with it. Okay, some e to the power I k phase vector. That is the similar thing. If you have certain two levels, then there are phases associated with these particular species, and if the phase difference between these two species is constant, you consider that to be a coherent superposition. You consider that to be a coherent regime. I'll talk more about this coherent when we move forward. Right now, it's not truly justified to bring this particular concept here, but you just understand that if their phase differences or phases are remain constant, or you have some particular phases associated with it, which is basically having certain phase relationship between the two species, then you can consider that to be a coherent superposition mixture. And in order to analyze now you have to solve the time-dependent Schrodinger equation. That is basically this particular thing, time-dependent Schrodinger equation. And you pretty much know it. If you solve it, you get a factor, you get a psi of t dependence as to be around approximately e to the power some minus I h t, where this h is basically the Hamiltonian of the system. And if you can write, for example, a Hamiltonian to be just energy, you can write it as energy e to the you can just write it in terms of energy, or you can just write it in terms of, let's say, for example, the Hamiltonian can be write in terms of what is energy? Energy is h bar omega. No, let me just write it like this. You will get confused. So you can just write it in this form if you solve this particular differential equation. Obviously, there will be some coefficients. Let's not talk about it. Oh, we made a mistake. So you'll get something like e to the power I omega t. Oops. And omega will be basically e over h bar, something like that. Where this is basically Hamiltonian. If it is simple energy, then you can write E. If it's actual Hamiltonian of the system, you have to write H. So it will be something like e to the power I H t divided by H bar. So this is basically the time dependent part. It's almost like a time varying part associated with the wave function. So actually this time dependent part, which is e to the power I omega t, is associated with the wave function. It comes from solving the Schrodinger time dependent Schrodinger equation. And now whenever you have a time-dependent system, what you need to know in order to see its time evolution is you need to know its Hamiltonian. What is Hamiltonian? It's some kind of a total energy of the system. It's a total energy which consists of the potential energy, it consists of the kinetic energy part. That's as simple as that. Okay, so if you know it, you just have to put it into this particular equation. But the issue is this Hamiltonian can be a matrix. Okay, it can be a matrix. Why it can be a matrix? You need to go into back into some matrix mechanics if you want to solve these particular problems. And it makes it easier because if this Hamiltonian is a matrix, then you can write e to the power minus I h t. Let's say this is matrix h t over h bar. If this is matrix, then it's basically a matrix exponential. Matrix exponential. And if you guys are interested in solving the matrix exponential, you can solve it using any of the software tools, or even if you can solve it using pen and paper. You can expand the exponentials in terms of I should say its series. You can expand it in terms of the series of the exponential, and you can write its Taylor series expansion. And what is important to note is that sometimes if this Hamiltonian is simplified, if it has only diagonal terms, then it becomes easier to solve the matrix exponential. But most of the time, if you solve some quantum system, this Hamiltonian is most of the times a complicated, huge matrix. Then you need to take the exponential of the matrix, and that is a little bit computationally expensive depending upon what is the size of the Hamiltonian. Okay, so that is how you solve it. And but if you solve this particular system, if you apply the a time dependent Schrodinger equation to this particular system, you get the solution as these. This is what you get as the solution. Not the solution. These are the, I should say, coupled differential equation. The solution is a different thing. These are the coupled differential equations. So what you have applied the time derivative on the probability distribution C1 and the time derivative on the probability distribution C2, and you get a coupled differential equation. That means there's a dependency. C1 of t is dependent on C2 of t. C2 of t is dependent on C1 of t. So these are coupled differential equations, and they are coupled in time. You see, they are all time dependent. They are all time dependent terms. So this e to the power I omega minus omega naught t comes because of solving this. That's why I told you can just solve this and you get this e to the power some this factor, I omega t factor. And you know that you can write this omega in terms of the energy. You can go back and forth. So these are the coupled differential equations you need to solve when you apply the time-dependent Schrodinger equation separately on the probability distributions. And the solutions you get when you solve them is either sine and another one is cosine. So if you solve it, you get C2 of t, let's say C2 of t to be approximately proportional to sine of something t, and you get C2 of you get C and you get C1 of t to be around cos of t. So this is not minus, this is t. There is some other factor. It's like omega r factor. So you get the solutions to be actually C2 of t, you get it sine of omega rt, C1 of t, you get cos of omega rt. Just need to solve the coupled differential equations. And this omega r is basically something called as, it's a frequency. It's like sine of omega t. So it's like sine of omega rt. So this omega r is basically the frequency which is given by this particular factor. And this particular frequency is called as Rabi frequency. So it is the frequency with which it is oscillating back and forth. So what is oscillating? The probability. We are finding the probability. This C1 of t and C2 of t is basically the time evolution of the probability distributions in state 1 and state 2. And what does it mean? It means that there is flipping of these states. It goes up, it goes down, it keeps on moving like this. So that is basically something called a Rabi frequency. So earlier, what you would have thought is that it would the some species will go higher and then it will decay exponentially. So you would have thought it would look something like this. But what quantum mechanically solving this Schrodinger time-dependent Schrodinger equation tells you that it's not actually happening like that. There is a frequency, oscillatory behavior happening. The species is going higher, then it's coming down, and the probability of transitions is changing. The probability transitions is changing. So let's say, for example, if some species starts at some even level, then it goes to E2 level. Let's say it goes to this level. What's going to happen is going to oscillate back and forth for some time. What is that time? We can also calculate that. And here we are totally considering the system to be ideal. It's almost like as ideal as possible. There are no dissipation forces. There are no dissipation mechanisms present in the system. It's almost like an isolated system. Okay, it's like almost like a closed system. So almost like a closed system, wherein there is no impact of the environment on this particular system. Only then you can observe these oscillations. Otherwise, if there are some dissipation mechanisms, let's say for example the electron dissipates its energy to the maybe in the form of phonons or in the form of non-radiative mechanisms, even in terms of radiative mechanisms, then these oscillations will look like something like this. These will decay with time. That is what basically we will show in this particular upcoming picture. What is going to happen to these oscillations if there are dissipations present in the system? So these are right now looking like a pure sinusoidal oscillations, wherein there is flipping of the probabilities from max to minimum, from max to minimum. Okay, and at this particular point, you see that the probability is half. That means the probability of occupation is exactly half. That means 50% of chances there are 50% of chances that you find these species in level level 1 and 50% that you find in level 2. That is what basically this point represents. Exactly this point. Yeah. So here the probability is exactly zero point 0.5 wherever they overlap these sinusoidal curves. I think that might be one of the questions in your assignment problem. And what is interesting to note is that, so how is it happening is that basically, if you have, let's say, a closed type of a system wherein these two levels are there, then what you get is that you get these oscillatory behavior, what you call as a Rabi oscillations with the frequency of Rabi frequency. So actually what is happening is that the electron is going higher, then it is coming down, it is emitting some photons, but that photon is getting reabsorbed, and that is again causing some kind of a excitation, and then it is oscillating back and forth. So it can only happen if you have some kind of closed system. If there is no dissipation, if there is no uh, environment interaction over the system. But what is going to happen if you, let's say, open the system? If you have now open system, are you going to see this kind of a oscillation? It's very difficult because these oscillations are going to decay very fast. Okay, let's say for example, in an open system, let's say for example, this will go down, the photon is getting emitted, then this photon may get absorbed by maybe a cavity, or this may get absorbed by in the environment, then you no longer will see these particular oscillations. So it is really difficult to see these oscillations experimentally unless and until you don't go at some kind of a geometry, or at a lower temperature rather. That is why most of the people get confused at why you don't see these Rabi oscillations. But people are right now doing experiments in the physics community in order to observe these experiments, and they have different implications in order to understand the fundamental physics. Okay, and later on we will see that why is it easier to see certain Rabi oscillations in certain species. So that is the point. The probability is basically oscillating sinusoidally between the two levels. And now, if you want to, let's say, find the time period of oscillation, if you talk about this particular time period of oscillation, which will be the inverse of the Rabi frequency. If this is the Rabi frequency, so the time period of oscillations will be inverse of the Rabi frequency. So it will be around something like h bar divided by mu12 epsilon naught. Mu12 is basically the dipole moment. And you know the dipole moment is charge times the distance between the two species. If let's say we use one angstrom value of the distance between the two species, then you get a dipole moment to be around 10 to the power minus 29. And you can find the Rabi frequency that comes up to be 10 to the power 8 radians per second. If you inverse it, you get the time period of oscillations to be around 0.6 nanoseconds. Okay, so how much is it? It's around 0.6 into 10 to the power minus 9 seconds. Or in other words, you can write it in terms of, let's say, 600 picoseconds. So this is the time period of oscillations. You see, it's very short, 600 picoseconds. It's not shorter, but I would say it's short time period. But what you have to do in order to increase this particular oscillatory time period, a simple picture tells you that if you want to decrease the period of oscillation, you increase the E naught, where E naught is basically the electric field. Electric field amplitude. Which electric field? Electric field of the electromagnetic wave, whatever is perturbating it. The perturbation field. Okay? Increasing the electric field means basically increasing the intensity of the electromagnetic beam, because intensity is directly proportional to amplitude electric field square. Okay? So if you want to just increase the electric field, the period of oscillations is going to reduce because it's inversely proportional, or the time period is going to increase. So now what? Now what is going to happen is that there are certain scenarios wherein you can observe the Rabi oscillations or wherein you cannot observe the Rabi oscillation. Let's say, for example, if you take a case wherein this time period of oscillation is basically 20 nanoseconds, which is the inverse of the Rabi frequency. And if you have a radiative decay lifetime of 2 nanoseconds, that means faster decay even before the Rabi oscillations will be observed. So that means if you have a two species, this is level 1, this is level 2, the electron is going here, and if it is going down and the radiative lifetime decay is 2 nanoseconds, that means your species is decaying even before the Rabi oscillations have started. I mean that because the time period of oscillation for the Rabi frequency is like this. So this time period is 20 nanoseconds. And before 20 nanoseconds, let's say here, 2 nanoseconds, the species is decaying. So are you going to see the Rabi oscillations? Obviously not, because even before the oscillation will start, your species would have decayed. It would have decayed and emitted some kind of some photon, and that photon might be absorbed by certain things. So that is the fundamental thing. Your time, if you want to observe it, your time period of oscillation should be at least in the range of the radiative decay lifetime, or it should be at least much smaller than the radiative lifetime decay. So that's why in this particular case, there will be no Rabi oscillations seen, because the radiative lifetime decay, the decay time is much greater than the Rabi oscillation time. So now there are two things. The damping basically happens. The damping I talked about, that if you want to observe these particular oscillations, you are not going to observe these oscillations as such. There will be oscillations something like this, and it will damp with time. There will be exponential decay. So it will be some exponential decay, sinusoidal exponential decay. Why does that happen? That happens mostly because of two processes. The damping happens because of either spontaneous emission, it happens either because of dephasing. So if we talk about spontaneous emission, that is the species decays to the ground state and emits a photon, and that photon just gets lost, and that can no longer excite its system. That's what I talked about. So if this is let's say this electron went up and emits a photon, then this photon can get reabsorbed and it can just excite the species back, and you get these oscillations. But what if this photon gets lost? So if it gets lost, then you don't have the repeating oscillations. So you will naturally find the oscillations to decay. So a closed system where other I should say this particular oscillations are mostly seen, that in a closed system where other mechanisms of dephasing or damping are totally neglected. But in actual world, we have an open system. So the system is mostly open. So that's why it's a totally different set of equations you need to solve for the open quantum systems. There's something called as open quantum systems, wherein you need to consider the system plus environment interaction. Okay, you need to consider the impact of the environment on the I should say system. So if I give you a simple example, when you solve if you want to understand let's say a transistor, that's a classical example. I mean, you guys know about transistor. Let's say for example, let me just show you here. If you guys know about transistor, then you know that let's say for example you have some source, you have some drain, and let's consider this channel to be made up of some atoms. Okay, then basically the transistor is this part here. The source and the drain, whatever is on the source and the drain, you connect the probes and you get the currents and the voltage out from it. But whenever you connect this probe, this is basically now making it to interact with the environment. Okay, you're connecting it to a different system altogether, you're perturbing it. So let's say if this was the system, then here this can act like an environment. So this will be like now whenever you connect a probe, you are perturbing or you're connecting the system to the environment, and you will find the system environment interaction. So if some of you if some of you know how to solve the I should say quantum mechanical equations for let's say a transistor using Green's function formalism, then you might be knowing that if you can find the Hamiltonian of this particular system, let's say you have a 1D chain of atoms, 1D chain of atoms, then basically what you can do is that you can write the Hamiltonian of this 1D chain. Okay, if you know the Hamiltonian of this 1D chain, you can write something called as Green's function. What is Green's function? That's a different story altogether. So you can basically write the some energy minus the Hamiltonian. Okay, so let's say for example let me write it like this. Some energy into identity matrix minus the Hamiltonian. This is just to satisfy the matrix dimensions. Let's not go into that detail. I will not confuse you. I'll just give you a layman picture. So if you know the Hamiltonian, you can find the Green's function. And if you know this Green's function, you can find something called a spectral function. And if you know spectral function, you can find density of states. If you know density of states, you can find N of E, which is the concentration. If you know N of E, you can find the current, you can find the voltage, and you all together know what's happening to the device. That is how you quantum mechanically solve it, how you quantum mechanically arrive at a current, voltage from Green's function, from the Hamiltonian, and all other things. What are these spectral functions? I don't want to go into the details, but this is how it is done. But what I wanted to explain is that how this environment interacts or how this environment perturbs the system. Whenever we want to talk about these environments or the contacts, we include it in the overall Hamiltonian. So this overall Hamiltonian gets changed, and you have something called as self-energy terms. Self-energy terms, which take into consideration the environment, the contacts or the probes. Okay, so the overall Hamiltonian, you write the overall picture gets changed and you write the overall energy terms, which are basically the self-energy terms. You write something like sigma 1, sigma 2, where this sigma 1 is because of this contact, sigma 2 is because of this contact. Okay, so these are self-energy terms because now it has connected with the environment, and they get into the overall Green's function. So you write overall Green's function as some E of I minus H minus sigma 1 minus sigma 2, its inverse. So if you can solve this particular quantity where E is the energy, I is the identity matrix, H is the Hamiltonian, sigma 1, sigma 2 are the self-energy terms because of the contacts or the environment interaction. And if you take the matrix inverse, you find something called as Green's function. If you know Green's function, you can find something called as you can find density of states, you can find spectral function, you can find if you know density of states, you can find the concentration, which is basically N of E is some density of states times the Fermi function. Or if you want to find N, you can just integrate these particular terms. You can just integrate these terms from some energy level, let's say EC to infinity, some energy levels. If you know N, if you know what is the concentration of the electrons, you know you can compute current. Simpler terms, the current is N Q mu E. This is I guess this is the current density, but it's one and the same things per unit area. Now you need to incorporate certain different things in it, but I'm just telling you in a simplified fashion. If you know current, if you know current voltage characteristics, you can just know anything about the device. So that's how quantum transport works, and that's how quantum mechanically things are done basically, and that's what system environment interaction basically does. Similarly, one way of losing or one way of damping the system is basically spontaneous emission. That's what I talked about. The other way is the dephasing. How does the dephasing occur? Dephasing occurs because of certain processes happening inside the system. Let's say, for example, electron-phonon interactions is one of the classical, I should say, one of the good example of how the dephasing happens. And what it causes, again, it causes the damping. Let's say, for example, the electron was here, and now it can non-radiatively recombine, and it can emit a phonon, and this phonon can heat up the system. Or a phonon can just come and just interact with the electron. It's something called as electron-phonon interaction, and that can cause the electron to lose its phase completely. The phase which the electron was having in this particular state, it will lose its identity. Not completely, but there will be some phase mismatch now. That's what is basically called as dephasing. Dephasing means that now the phase in state 1 and phase in state 2, the difference is no longer equivalent to 0. That means there is not the phase of phase 1 is not equivalent to phase 2. There is some phase lag or phase delay associated with now the wave functions of the electron present in these two species. And the question why does the phonon does it? That's a different story altogether because the phonons is basically the lattice vibration. So whenever if you have, let's say, for example, these atoms connected with the bonds, and let's say if you have an electron here, now if the atoms start to come closer, let's say this atom comes here, this stayed here, this atom come closer, so you have something like a compression here. So you compress the lattice. So it's almost like it is basically a phonon. Okay, it's a strain, but this is what a phonon can actually do. A phonon came in, a vibration of the lattice happened, or this lattice started to compress, and this can go on in an entire lattice in the form of a wave. So that is what you call as a lattice wave. And if you talk about that lattice wave in terms of quantum mechanics, you called it a phonon. Just like if you talk about electromagnetic waves, you talk of electromagnetic waves in a quantum realm, quantum domain, you call it as a photon. So that compression can basically change the electron's energy. That has an impact on the band structure. It can move it up, it can move it down, and so on and so forth. So that is how it can interact with the electrons. Whenever it interacts with the electrons' energy, you know that it can cause all sort of effects. Now, what is going to happen is that if you let's say for example, there is a quantity called as the damping ratio to that of the damping factor divided by the Rabi frequency, this particular factor. So damping factor divided by the Rabi frequency is the important parameter which you need to understand. So if the damping it is gamma to sigma r, the gamma to omega r is equivalent to 0, so you get no damping. If it is zero point 0.1, you get some sort of damping, but if it is 1, then you get a form of probability, something like this. It's almost as if it's not oscillating at all. So this particular thing is if it is zero point 0.1, if the ratio is zero point 0.1. And this particular thing is if the ratio is 0. That means there is no damping at all. And if there is, if for this particular case where there is a huge damping, that means gamma is exactly equivalent to omega r, then what you do is that you find no oscillations are observed. And in order to observe the oscillations in these, what you do, you have to increase the intensity of the electric field of the electromagnetic wave. That's what I talked about earlier. And then only you can observe the oscillations. Okay, so that is as simple as that. Now, what else is there? I think I explained a lot of stuff here on the overlay. The reason why I do like this is because it keeps me on track so that I can explain all of the things uh, in this page on this page separately. Otherwise, I just go off track if I don't do like this. Okay, so then moving into the experimental observation of the Rabi oscillations, I haven't talked about it detail, but how do you do it experimentally? Most of the people do it using microwaves in certain, let's say, gigahertz regime, because these are also electromagnetic waves. So if you can just hit a system with certain microwaves, microwave pulses, and those pulses are basically controlled, their phases are controlled, and the pulse widths are controlled. Just like for example, here you have an example where you have the fluorescence on the y-axis and you have the pump pulse area on the x-axis, and you get a fluorescence peak at certain phase, which is pi, a certain pulse area, which is pi, and you get a dip at certain 2 pi, and then you get a increase at certain 3 pi. That means you get an increase at certain odd pi's, and you get a decrease in fluorescence at certain even pi's. Okay, so what does this mean? This means all atoms, like, these are in excited state, these are in lower state, excited state, lower state. So that is basically what fluorescence measurement gives you. And now if you talk about what is this pulse area, the pulse area is given by this particular quantity. Okay, and it's almost like a dimensionless quantity. Now this is like an ideal pulse. It can be a microwave pulse. It's like a pulse envelope basically. It's not the actual pulse, because actual frequency is oscillating at a much higher frequency. It's the envelope of the pulse. Let's say, for example, if you have a laser, something called as femtosecond laser. Femtosecond laser is a laser which emits the laser beams, but in pulsed fashion. Let's say, for example, it emits the laser beams like this, this, this. And the fascinating thing about it is that each pulse is of the order of some femtosecond, let's say 50 femtoseconds. So the pulse width of each is 50 femtoseconds. That is very, very small, of the order of, it's almost like a billionth of a millionth of a second. Okay. And these pulses repeat at certain time interval, which is basically, let's say it's 1 kilohertz. That's basically repetition rate of these pulses. But when you talk about a single pulse, let's say if you talk about a single femtosecond pulse, it can be a femtosecond pulse, a light pulse from a laser. It can be even a microwave pulse. You can do it with the microwaves as well. But if you talk about a single pulse, you can zoom it, and you can basically zoom it like this. So this is femtosecond. The FWHM is femtosecond. And this is basically the envelope of the pulse. Whatever the red is showing you, that is basically the envelope of the pulse. The actual electric field of this of the actual electric field oscillations are is oscillating at a much rapid rate compared to that of what the envelope is showing. So actual electric field looks something like this. So if this is, let's say, if this is 50 femtosecond, then the actual electric field time period, or the width, is much shorter, can be around, let's say, 2 femtoseconds. It depends upon what frequency are you using. If, let's say, these femtosecond pulses let's say, are in the wavelength of 800 nanometer, then accordingly you can find, let's say, the frequency of these oscillations as c over lambda, and the time period will be lambda over c. So if you find this time period, it will be around 2 to 3 femtoseconds. So this is the time period of the internal oscillations, actual electric field oscillations of the inside this femtosecond envelope, inside this femtosecond pulse. Okay, so that is much faster. But we are talking about here the envelope. Okay, and now what is going to happen is that if you control somehow this pulse area, whether it's in microwave, and if you make it of the order of pi, of the order of 2 pi, then you can play with the fluorescence of the atoms. And and obviously we have seen that in order to observe the Rabi oscillations, this condition needs to be satisfied. That means the Rabi frequency needs to be much greater than the decay rate. That is the exact scenario. Because if it is much smaller than the decay rate, if it is, let's say, for example, if the species is decaying much faster than the Rabi oscillations, then you are not going to observe the Rabi oscillation. That's what I talked about previously. Now, there is certain, let's say, for example, gases. This gamma is of the order of 10 to the power 7 to 10 to the power 8 per second. For gallium arsenide, it's quite small. So that's why it's very difficult to observe in semiconductors, and it's very easy to see these particular things in gases. And another example, then professor might have quoted about the side bands of the Rabi oscillations. The Rabi oscillations is just like it's almost as if the single level of an atom is basically splitted with the splitting equivalent to the Rabi frequency. The energy is frequency, and frequency is energy. That's one and the same thing, just multiplied with the Planck's constant. And similarly, the upper level gets uh, splitted into two levels with the splitting of the order of Rabi frequency. So that's why you see two bands in these particular fluorescence pictures, and you get the side bands at omega naught minus omega r and omega naught minus plus omega r. So what else? Now we move into something called as atom cavity interaction, and we talk about something called as weak and strong coupling regime. So what we are going to do, we stopped here, we'll stop here, and we don't go into the further details of the Rabi oscillations. If you guys are interested, you can just, particularly if you guys are interested in the maths of it, you can just see Griffith's Quantum Mechanics, Introduction to Quantum Mechanics by Griffith, Introduction to Quantum Mechanics by Griffith, and you can see the chapter for on Rabi oscillations, Rabi flipping. So this is actually the Rabi flipping is going back and forth. That is basically what is meant by Rabi flipping. Mostly that is used in the NMR terminology, wherein you play with the spins of the protons of the hydrogen atoms. But the concepts are similar. And if you in NMR, the concept is that you flip the spins with the microwaves. Okay, and that basically helps you. The detuning is almost something like this. Then there is dephasing, and that basically the response comes from a different hydrogen atoms present inside the water molecules of our brain, because mostly our brain is composed of fluids. So that basically helps you to reconstruct the image by capturing the signal in a three-dimensional pattern of our brain. I'm just giving you the overview. If you guys are interested, there are a couple of cool videos on the YouTube as well, which basically show the schematic or even the mathematical explanation of these nuclear magnetic resonance techniques. So nuclear means they are playing with something like a nucleus. That's why they are playing with the protons. They play with the spins of the protons. That's why I have shown this image particularly here. So whenever you hit whenever you hit some electron with some kind of a microwave, the spin kind of it kind of wobbles, kind of I should say there is some kind of a detuning associated with it, and then it comes back to its original position. So that's what basically this represents. Okay, so it's a field which is basically most closely related to spintronics also. But the set of equations are also same. You also talk about Rabi flipping, Rabi frequency in those particular areas. Okay. Now, if we talk about atom cavity interaction, earlier what we talked about, we had a nanosphere. We had a nanosphere, plasmonic nanosphere, and then we talked about the cavity. We talked about how the electromagnetic wave will interact with this. So there will be some negative charges induced, some positive charges induced. You talked about sigma, the induced polarization charges, and you talk about that it is dependent upon the permittivity of, let's say, epsilon 1, epsilon 2, and we have all together talked about these plasmonics in the previous lectures. Now here we will talk about what is going to happen if we put some kind of atom inside a cavity. Okay, so you guys might be knowing about certain concepts like the Fabry-Pérot cavity, the concept that if you have the photon bouncing back and forth inside this particular cavity, so it will build up inside the cavity, and at certain integer values there will be constructive interference, and at certain I should say odd integer values there will be destructive interference through the round trip. And what basically happens is that the intensity gets built up inside. So intensity increases. That means if there are 100 photons built up, and even if 1% of the photons escape, then it will be a huge intensity. So that's how you build up the intensity in the Fabry-Pérot cavity. And particularly, these are very useful in interferometers. I have worked on one of the Fabry-Pérot cavities in a Michelson interferometer. So if you have an interferometer, you can just increase the amplitude by making a Fabry-Perot cavity, which is made up of certain mirror configuration, and the light goes back and forth, and then increases in the amplitude, and then the light comes back, and you can just altogether have a huge amplitude of the light. And these are mostly also used in most of the interferometers in order to increase the responses, but they are obviously used in nanophotonics. And what is the important concept here is that uh, the important concept here is the if you talk about the this particular cavity, then it has certain length, which is basically the length of the cavity, and the the delta omega. Let's say, for example, this cavity, and it is transmitting something after multiple reflections. It's transmitting something. That transmission is basically shown here, and you get transmission at certain. Okay, so what I was talking about that this is a transmission spectrum which you get from a Fabry-Perot cavity, and the the line width of this transmission spectra is inversely proportional to the time period that a photon spends inside the cavity. And obviously, this time period would be dependent upon the length of the cavity. That means it will be the tau cavity would be around some the length of the cavity divided by the velocity of the photon inside the cavity. And that means this line width is dependent upon the dimensions of this particular cavity. So the photons stay inside if the photons stay for inside the cavity for a long time, you will get a high Q factor. What is the Q factor? The Q factor is how sharp this particular peak is. That means it is the ratio of omega over the line width. So if the line width, let's say, reduces, the quality factor will increase. That means it will become sharper. It'll become almost like a delta function. So that is what quality factor tells you. You might have heard about the quality factor resonance also. That tells you about how good a resonance is. And how good a resonance is basically implies how sharper that particular, I should say, how higher the quality factor is, or how sharp is this peak. Okay, so this is the essential thing, that if you want to improve the quality factor, what you need to do, you need to reduce this particular line width to increase this quality factor. And how do you reduce the line width? How do you reduce the line width? You increase the tau cavity to reduce the line width. In order to increase the tau cavity, you need to increase the length of the cavity. In order to increase the tau cavity, that will reduce the line width. Reducing the line width will increase the quality factor. So that's what basically is represented here. So now what is happening if you place now a two-level system inside this cavity? Earlier you didn't have any two-level system. Now what is going to happen? There will be interaction of the light or the photons with this two-level. And that photon can get absorbed, that can get re-emitted, all sorts of effects are going to happen. So let's say if you have a cavity, which are these are two mirrors, and there is some coupling factor with the atom cavity coupling factor. That means the coupling of the light with that of the atom. This G naught takes place of that, how the coupling takes place, or how much is the coupling. Gamma is basically some decaying factor. For example, if there are some species in the excited state, they will just decay spontaneously and radiatively. That gamma will take into consideration. So there will be a radiative decay, let's say, or even non-radiative decays, and the kappa will take into consideration the cavity decay rate. That means if some photon is generated, that will just leak out from the cavity and then go into the environment. So now there are two scenarios. If this G naught, that means the atom cavity coupling, that means the coupling of the photons with that of the this two-level system. If this G naught is much less than the kappa and gamma, then the atom releases a photon and this is lost from a cavity. So this is first of the scenario. That means whatever the photon is released by the atom, that gets lost from the cavity, because these factors are huge. The kappa is huge, that means the photon will get lost. The gamma is huge, that means there will be some maybe non-radiative decay. The electrons will decay non-resonantly even, and they will just give rise to phonons and will heat up the system. You will get you will lose the photons. Okay. Now there is another scenario. If you have a strong coupling, that means the photon is coupled to a two-level system strongly. That means this G naught is much greater than the cavity decay rate and the non-radiative decay rate. That means much greater than kappa and gamma. So in that case, you will have strong coupling of the photons with that of the two-level system. In that case, the atom releases a photon and photon interacts with the cavity and re-excites the atom. So that is the particular scenario because this G naught is huge. It's almost like a coupling factor between a photon and a two-level system. So first, if we talk about the weak coupling regime, we talk about something called as Purcell effect. Even we talk about Purcell factor. So the question is, does the cavity play any role in this? Yeah, obviously we saw that if we talk about the length of the cavity, that is basically going to control the time with the time the photon spends inside the cavity or the cavity time constant, and that in turn is going to affect the quality factor of the cavity. That's because this is going to affect the line width of the transmission spectra. So you see that this particular quality factor depends upon the omega, which is basically the frequency, and the kappa, which is basically the this kappa, the decay rate, cavity decay rate. So if you know the cavity decay rate, you are going to compute the, if you know the quality factor, you can compute the cavity decay rate, knowing the frequency and knowing the quality factor, obviously. Then we define something called as Purcell factor. What is Purcell factor? It's basically the decay rate in the cavity divided by decay rate in the free space. That means, let's say, for example, if you have a cavity and if you place some kind of a quantum dot inside, which is basically emitting a photon, so what will be its decay rate compared to if you have a quantum dot in a free space, if it emits a photon, what will be its decay rate? So that is the Purcell factor. So it is like the decay rate in free space and the decay rate in cavity, its comparison or its ratio. So if you compute it mathematically, you can just see it in the book. We don't go into the derivation much. You arrive at this particular relation where the Purcell factor basically depends upon the quality factor. It depends upon the volume, the volume of the cavity. So the smaller volumes the gives the or the higher quality factor gives the largest Purcell factor. So you want to increase the Purcell factor as much as possible because you want to have the high quality factor and you want to have the smaller volumes of the cavity. That's what you do. You want to miniaturize it and you want to get the huge quality factor. And it also depends upon the wavelength of the photon you are going to consider. So if, let's say, for example, the Purcell factor is much greater than 1, so you have enhanced spontaneous emission. So if Purcell factor is much less than 1, so the spontaneous emission is inhibited. That is basically the concept. That means if the wavelength falls in the photonic band gap region, then there are no states to emit, and the spontaneous emission is basically emitted, and it provides the non-radiative decay, provided obviously the non-radiative decay rates are smaller. So what does this mean? It means that if the Purcell factor is much, much less than 1, what does it basically imply? That it would imply that the I should say the volume, it can happen if the volume is much, much huge and the quality factor is lower. Is it so? No, it would happen if the volume is much, much, let's say, smaller, and the quality, it's opposite. The volume, if the volume goes on much increasing, then the denominator will reduce the increase, then the overall the Purcell factor will become much less than 1, and you will notice that the spontaneous emission will get inhibited. What does that mean? That means the wavelength which you are talking about falls in the photonic band gap region. That means if you have some photonic band gap inside this particular cavity, then you will notice that the particular wavelength you are talking about will fall in this photonic band gap region, and you no longer will have the spontaneous emission if this Purcell factor falls less than 1. But if it is greater than 1, then you have the enhanced spontaneous emission. That means there are a lot of density of states in the cavity and they decay faster. And obviously we're talking about here the photonic density of states, just like electronic density of state, and we talked about it in the previous lectures. Now again, we won't go into the details, but there is some question: what if you have a quantum dot and you have a quantum dot present inside on a crystal, and this quantum dot, it's you have some I should say some DBRs, which are basically repetitive arrangement of certain heterostructure layers. Basically, these are distributed Bragg reflectors. They just reflect the photon, whatever is generated inside this quantum dot, and this forms the cavity. So basically, these are two mirrors, and inside the photon goes back and forth. This forms the cavity. So it's almost like a two-level system in a cavity. So it's an example of cavity and cavity of photon atom interaction inside in a cavity. For it, you are given, let's say the emission wavelength is given, the radiative decay time is 1.3 nanoseconds, the volume of the cavity is given, the quality factor is given, and n, which is basically the refractive index, which was this n, it's the refractive index here. So it is also given. You need to find the Purcell factor. So you can simply find the Purcell factor, and if you know the Purcell factor, you can find the tau cavity. That means how much time it spends in the cavity decay rate, and that can be given by the how much is the radiative time divided by the Purcell factor. Okay, why it can be found out? Because of this ratio. Okay, so because the Purcell factor is decay in a cavity, decay in a cavity divided by decay in free space. Okay, so you get the tau cavity to be 50 picoseconds. So what does it mean? That means if you have a quantum dot in a free space compared to that of a quantum dot in a cavity, it's going to decay faster in a cavity compared to that of in a free space. You see the tau r is 1.1 nanoseconds here, but the tau r it gets changed when you place that particular I should say atom inside the cavity. It gets reduced to 0.25 nanoseconds. And this faster decay is really important in case of certain sources, which are something called as single photon sources. You want this to be as fast as possible and in order to get a on-demand photons. So this is basically a PL intensity, photoluminescence intensity. This is a luminescence spectra. So what else? So that's what I have shown here. To create the single photon source, you place a quantum dot, let's say in a two-dimensional photonic crystal. So if a quantum dot is separate, you get a increased decay time. But if it is in a cavity, you get a faster and it approaches almost to a single photon emission. So this should be as fast as possible for a single photon emission. Now, what happens in a strong coupling regime? I told you that for a strong coupling regime, this coupling, basically the coupling of the two levels to in a cavity, this is much greater than gamma and much greater than kappa. Let's present kappa as like this. This is kappa. Then what is going to happen is that your levels will interact with the photon and they will hybridize and there'll be splitting of energy levels. Okay, so the professor might have talked about the sodium atoms getting splitted into two levels, and you will observe that because of the huge interaction between the photons and the atoms. So you might have seen a similar example when you talk about the plasmonic nanosphere on certain substrate, certain substrate where the gap region holds the electric field, which is the light confined in the gap region. So you might have seen also the strong coupling there, and you have the splitting of these particular peaks. So that we have all talked about. So we won't be going into the deeper explanations of this strong coupling regime because it's a very I should say there needs to be deeper explanations in order to understand and explain each and every concept. But the professor has tried to give you a flavor of each of these mechanisms or concepts so that you can basically go and check and you can relate whatever we are studying is basically going to be useful in understanding, let's say, a single photon sources in quantum communication and all other things. So this is the physics behind it. And we're not going into the details for a reason. Okay, so now what? We are going into the questions. So now if we talk about the questions, the first question is where's the first question? Okay, so I guess first question is missing here. So we're directly starting from Q2, Q3. Let's see if we can go to the first question at the end. And the first question says that a Fabry-Perot cavity is generally made of two mirrors. That's what I talked about. This is a Fabry-Perot cavity. The light goes back and forth. Okay, and some light emits, and we compute the transmission spectra, and this is basically the transmission spectra shown here. Okay, so it shows the transmission spectra of three Fabry-Perot cavities A, B, and C, whose photon lifetimes are given as tau A, tau B, and tau C. So the photon lifetimes tau A, tau B, tau C. We talked about that this tau is basically inversely proportional to that of the line width, which is this line width. So that means if the line width is large, the photon lifetimes will be smaller, so on and so forth. And from the transmission spectra, Which cavity have more reflectivity? So we need to understand which cavity have more reflectivity from the transmission spectra. How do you understand that? Understand that from a quality factor. If the quality factor is more, that means there will be huge reflectivity inside the cavity. And the quality factor depends upon omega over delta omega. Okay, so if delta omega is less, the quality factor will be more. That means the reflectivity will be more. So the delta omega is less for this red one, which is this. So the delta omega for red is less than delta omega for blue is less than delta omega for green. That means the quality factor for red is greater than quality factor for blue is greater than quality factor for green. That means the reflectivity for red is greater than reflectivity for blue is greater than reflectivity for green. Because the reflectivity inside is going to build up the photons inside it and is going to build up the intensity. So the intensity is going to increase and the quality factor is essentially going to increase. Okay, and that means the red is the answer of this question. I'm just drawing it with the red itself. So now what can be deduced about the photon lifetimes from the transmission spectra? You know that photon lifetime is inversely proportional to the line width. So it will be opposite. So if the red was having the highest reflectivity or the highest quality factor, then the red will be having the lowest photon lifetime. That means what is red? Red is tau c. That means the tau c would be about the photon lifetimes. Let's say, for example, the quality factor is omega over delta omega, and this photon lifetime is inversely proportional to 1 over delta omega. So if delta omega for red is much smaller than delta omega for blue is much smaller than delta omega for green, that means the tau red is greater than tau blue is greater than tau. Oh, no, let's try it. That means this is 1 over tau red, this is 1 over tau blue, this is 1 over tau green. If you if you just flip it, you get tau R greater than tau B greater than tau G. I guess this is A, this is B, this is C as per the notations. So the answer of this question should be, I guess we have done it opposite way. Yeah, I guess we have done it in the opposite sense. So if you talk about the photon lifetimes inside the cavity, photon lifetimes of the cavities A, B, and C from the transmission spectrum, then it is going to follow that the the lifetime for the photons inside the cavity for tau C is going to be greater compared to that of the tau B compared to that of the tau A. Let me just cross check whether we are really doing it correct or not. You just give me a moment. Okay, yeah. So the concept is it's inversely proportional. Obviously, it's inversely proportional to this. So the broader this means shorter time period. Okay, that means tau A will be smaller and tau C will be larger. Why? Because delta omega C is small. That means tau C will be large. Okay, I guess there was a confusion about, I guess, yeah, we had earlier done it in the similar fashion. It's inversely proportional, obviously. I got confused with something else. But yeah, that is the answer of this question. Okay, is there any ambiguity in this question or not? Or am I just overthinking on it? It's just like a simple relation, and if you have a broader spectrum, broader line width, then you have a tau c to be large, and that particular tau c will be large. Yeah, that is the exact answer. I was just cross-checking the question. Okay, so consider two gaseous species with two separate cavities in a two separate cavity. So you have certain cavities and you have certain gaseous species present here. This is cavity A, this is cavity B. The gas in a cavity has a time period of Rabi oscillations of 2 nanoseconds, and cavity spontaneous decay rate of 20 nanoseconds. For the gas in cavity B, the Rabi oscillations are 20 nanoseconds and cavity spontaneous decay rate is 2 nanoseconds. In which case do you expect to observe the Rabi oscillations and why? Obviously, if you want to observe the Rabi oscillations, this decay rate should be greater than that of the Rabi oscillations rate. That means for this case, 20 nanoseconds, this 2 nanoseconds is much smaller than 20 nanoseconds. You are going to observe the Rabi oscillations. Okay, so it's almost like this, this, and if this, let's say, for example, let me just draw it like this. If this particular time period of oscillations, Rabi oscillations, let's say 2 nanoseconds, then the decay rate is almost like 20 nanoseconds. Then you are going to at least see 10 cycles of the Rabi oscillations before the gas or the species in cavity A will decay. On the other hand, for this particular thing, the decay rate is faster. It's 2 nanoseconds, which is much faster than 20 nanoseconds. You are going to have a spontaneous decay of the species faster than the Rabi oscillations can happen, and you cannot observe the Rabi oscillations. So the gas in cavity A, because tau r is much greater than the Rabi oscillation period. That is the exact answer of this question. That's what we even talked about. Now consider a resonant cavity with the volume and quality factor and wavelength resulting in the Purcell factor. We talked about what the Purcell factor is. It's basically the decay rate in cavity for an atom or whatever species you're talking about divided by decay rate in free space. If the volume of cavity is increased by a factor of 4 and quality factor is increased by 3 at the same wavelength, what will be the new Purcell factor? So you talked about the Purcell factor relation, which is approximately proportional to Q over volume. And there are some other factors which depend upon lambda cube divided by n cube and some other constants. So what it is saying is that use at the same wavelength, so we are considering the wavelength to be constant, and they are increasing the quality factor by 3, and their the volume of the cavity is increased by factor of 4 and the quality factor is increased by 3. So what will be the new Purcell factor? It will be 3 by 4 times the old Purcell factor. So that is the answer of this question. Because the quality, it is directly proportional to quality factor and it's inversely proportional to the volume. That's as simple as that. Okay, so which of the following are true in nanofabrication? Let's not talk about nanofabrication in this particular session because I have not gone into the nanofabrication processes. That's a separate topic altogether. We will talk it in upcoming sessions or next sessions. Okay, so I guess the question 1 and question 6 are based on nanofabrications. So let's deal it within the next sessions because they are altogether different. And I guess Professor has done a very good job in explaining these. Okay, so the answer of this question, I'll still say that lithography is used to pattern the system and ellipsometry is used to measure the thickness and optical constants. Yes, that's the answer. Lithography is just like if you have a substrate and if you have a pattern which you want to imprint on the substrate. If you want to imprint this pattern on the substrate, you bring in some UV lights and that gets imprinted on the substrate and this pattern gets imprinted on the substrate. So that is basically lithography. It's used to make the patterns on the substrate. That's how your chips are made. And it's mostly done at a company called as ASML, Advanced Semiconductor Manufacturing Limited. That's in Netherlands. It's the only company that has this particular capability to manufacture nanometer scale lithography using the sub ultraviolet light systems. It's very costly. That's why only a single country is having a monopoly over it. And I won't go into the nanofab details. Okay. So if we place a quantum dot in 3 different environments, what will be the order of ready to decay lifetimes in 3 of the environments? I talked about a cavity and atom interaction. Whenever you place certain quantum dot in a cavity, then the decay will be faster. So decay will be faster. So that means if you have, let's say, a photonic crystal, and if you have an aqueous medium, if you have a vacuum, this is vacuum. So in this, the decay will be faster compared to that of this, compared to that of this. So that means ready to decay, tau photonic crystal will be smaller than tau aqueous, that means it will be smaller than tau vacuum. That means tau vacuum, the radiative decay will be huge. It will take a longer time for the species to decay compared to that of in aqueous, compared to that of in photonic crystal. Photonic crystal is almost like a here it's almost like a system or a cavity. So what is the answer of this question? So this is the answer of this question. So whenever you talk about, let's say, you know, you can place a quantum dot in a photonic crystal that you have seen. But what about aqueous? Basically, there are certain solutions of you can make a something called as colloidal quantum dot solutions of different colors. That is mostly in liquid form. You can have a liquid form of a quantum dots. That's something called as colloidal quantum dot solutions. And most of the time, those of you who work on laser systems or any of the optical systems, that is used as a benchmark or a reference in order to understand what will happen with the other species when you just start the measurement. So it's as a reference, something called a reference sample. So that's something called as colloidal quantum dot solution, and it's an aqueous solution. It's almost like a liquid, but therein you have the colloidal form of the quantum dots. So that is as simple as that. And another one is semiconductor quantum dot emits 900 nanometer, and the radiative lifetime of this. The dot is placed in a gallium arsenide microcavity. Refractor index, the modal volume, the quality factor is given as this. Calculate the radiative lifetime in the cavity on the assumption that dipole moment is parallel to the mode field and that the cavity is exactly at resonance. These are important conditions, obviously. The dipole moment is exactly parallel to the mode field. And this particular question I have shown here, where it is. Uh, yeah, here. So this is the exact scenario. So you are being given wavelength, you are being given decay rate, volume, quality factor, refractive index of the gallium arsenide. You just have to use this particular equation, put in the values, and then tau cavity will come out to be around 50 picoseconds. I guess this should be the answer, around 50 picoseconds somewhere. Yes, so this is the answer of this question, around 50 picoseconds. So I've shown it, shown above already. Okay, so I've shown this particular in the examples. I guess the professor has discussed this particular example also. Which of the following conditions are required to achieve strong coupling in a system involving a quantum dot and a microcavity? Okay, so for stronger coupling, what do you need? You need a larger quality factor and a smaller cavity volume. That means a Purcell factor is basically Q over V. So you want to reduce the V and increase the quality factor in order to increase the Purcell factor. So that means the smaller cavity volume and the larger quality factor is desired for a stronger coupling in order to increase the basically the Purcell factor. So yes, okay. A student shines a laser light on a cavity or a gas atoms in a cavity with a square-shaped pi by 2 pulse. At the end of the pulse, the population in the atoms will be. Yeah, that's what I talked about. If you have a system of in a cavity wherein you expect the Rabi oscillations to happen, and that will look something like this. The probability distributions will be oscillating something like this. Then this is basically the pi by 2 pulse. This is like pi. This is again like 3 pi by 2. This is 2 pi. This is 3 pi, so on and so forth. And I talked about in this particular session, in the beginning of this session, that at this particular point, the probability is 0.5. That means both of these species, this is, let's say, this if this was, let's say, for example, C1, then this is C2, then there is a zero point 0.5 probability of C1 and 0.5 probability of C2. That means there's a 50% probability of species to be in higher level and 50% probability of species to be in lower level. Okay, so for the pi by 2 pulse. Similarly, for pi pulse, you will get the species to be in, let's say, ground state. For the 2 pi pulse, you will get to be an excited state, so on and so forth. It's going to move back and forth in the excited and ground states. So the answer is 50% in 1 and 50% in 2. That's the answer of this question. Similarly, if you just solve those equations wherein you have C1 of t to be proportional to cosine of omega r t and C2 of t proportional to sine of omega r t, yes, then you this omega r is basically mu 1 2 electric field amplitude divided by h bar, its square, I guess. Was it there a square? I don't think so. There is somewhat like this. And now you can basically find what is going to happen if the at the end of the pulse, because you have the cosine and the sine dependence. That is what basically is shown in this plot. And you can observe what is going to happen at pi by 2. You just put the values of pi by 2, pi, 2 pi, and 3 pi, 3 pi by 2. Then you are going to find the probabilities, time dependent probabilities. That is basically these C of t's. So this is C1 of t and this is C2 of t. Okay, so I guess that is it for this session. And I hope you guys have understood some of the key concepts in this. You don't need to understand everything because this is very you need to understand the deeper aspects of quantum mechanics for it, particularly the system environment interaction, the quantum equations in the open system, what happens there. You need to understand that, but you just need to understand that you just need to get the flavor of it in order to understand what basically happens during the light matter interaction. So that's it about today. Now, in the next week, we are going to move into the quantum mechanics of photons. We're going to talk about photon statistics. We're going to talk about single photons. What is the distribution of the photons? Whether it's Poissonian, super Poissonian. We are going to talk about correlations, something called a second correlation, second order correlation, first order correlations. So this is basically the photons in the quantum regime. We are going to move to a single photon picture. And you know that a single photon is a quantum mechanical entity. It's no longer governed by the classical equations or the classical physics. And then we're going to classify it on the basis of certain characteristic, certain, I should say, classifications of the light sources. So that's it about today. I guess we will, I'll see you back next week. Okay, thank you.